This video is a representation of our paper KPU-Net, Kernel Point Unet for 3D LiDAR Ground Segmentation. In today's world, precision in terrain modeling is critical for civil engineering tasks such as urban planning, road construction, etc. LiDAR point clouds provide detailed three-dimensional measurements of the terrain environment. For urban planning, they map the existing buildings and give information about where to build the next ones. For road construction, they can provide information to develop roads, bridges based on the elevation estimations. And for power and communications, it ensures optimal pole placement. The LiDAR data provided by the Timmons group was collected using Alta-X drone. As the drone follows a precise grid flight path, the sensor emits laser pulses and records every return, building a dense, high-resolution point cloud. Here is a cross-section from our dataset which includes rooftops, tree canopies, and roadways. To derive meaningful terrain models, we need to separate ground from non-ground, which we call it as ground segmentation.
When it comes to real-world data, there are challenges such as occlusion, clutter, and geometric distortions. And if you don't handle these factors carefully, it can affect the efficiency and accuracy of the point cloud segmentation. To handle this, we propose a deep learning-based architecture, which we call it as KPU-Net, Kernel Point Unet for ground segmentation.
In our architecture, we use XYZ point coordinates of the point cloud as the input, and then we have TNet, UNet, and segmentation modules where it will assign a label to each point in the point cloud, either as a ground or non-ground. Now let's consider individual components. First, we have TNet. In the point clouds, we assume that semantic labeling of the point cloud needs to be invariant to object scores such as translation and rotation. One solution is to transform this input point cloud into a canonical space. And in order to achieve that, here we use transformation net. We call it as TNet at the input level as well as at the feature level. Next, we have the UNet. It's a KP convolution augmented encoder decoder architecture where in each block we have kernel point convolutional layers, and those will learn global and local geometrical features hierarchically without losing any information. Next, we have the segmentation module. It's a feed-forward architecture with multi-layer perceptrons and convolutional blocks. It will assign label for each point in the point cloud, either as a ground or non-ground. Here we have utilized supervised learning paradigm to evaluate the performance of our model. Here are the results of our model on the sports food dataset. On the left side, you will see the ground truth, and on the right side, you will see the segmentation output of our model. Our model achieves over 98% accuracy and processing up to 226K files per second in real time. This makes our architecture well suited for large-scale civil engineering applications where accuracy and speed are both critical. Finally, we would like to thank IEEE IES for the SYPA for this opportunity.